So, last class we looked at the dead center synthesis using a crank rocker. We first looked at for a specific rocker displacement and then saw that we could use the same technique for a motion generation problem if it is a 2 position synthesis problem where the pole is locatable easily. Okay. If you can use the pole for synthesis, then you could use that as a rocker output. The 2 position motion problem, motion generation problem can be converted to essentially a rocker output problem, and then you can design the driver dyad or the crank and the connecting rod in order to enable that to move between these 2 limit positions. So, that is what we looked at last time. Okay. In some cases it may happen that the pole may not be in a convenient position. So, you may not be able to use the pole to, so if this is say A1, B1, A2, B2, then it may happen that your only option is to use a 4 bar, that you cannot use. So, if I can locate that, and then for I can draw the perpendicular bisector of B1, B2, okay, and I can locate OA anywhere on this line and OB similarly anywhere on this perpendicular bisector, so that my linkage becomes OA, A1B, B1, OB. Ignore the fact that it passes through A2 here for some reason. Okay. Okay, so this becomes my linkage. So, I can move it, it will move from A1 B1 to A2 B2. However, I cannot, the way it is now, it is most likely a non-Grashof linkage. If you look at the dimensions, it is likely that none of the links are going to be able to make a complete rotation, and not only that, it is likely that these 2 are not limit positions. So, OA A1 and OA A2 are not limit positions. So, if I want to limit it to those 2 positions, now what do? I can just ignore the rest of the linkage and just look at OA A1. So, if I look at OA A1 and OA A2, okay, if I restrict the motion, say that is my input link, if I restrict OA A1, that link to move between these 2 extreme positions, then essentially I am restricting A1 B1 moving to A2 B2 and back. Okay. So, this basically reduces to the first problem that I solved, which is the rocker moving through this angle theta. Okay. So, now I can pick any point on this link or on this body when I can extend it, but let us just say I pick a point here, I call it C, C1, and the corresponding point would be C2. Okay. Then all I need to do is C1 C2, extend it pick my, what do I pick here? Some, I can call it D, some fixed pivot, okay. Then half of C1 C2 will give me D1 and sorry D2 and D1, okay. So, OD D2 equal to OD D1 equal to half of C1 C2. And so, this, so I am adding these two links now, okay. That is why we call it a driver dyad for two links, OD and CD, okay, D to CD. So, OD and CD, when I add it to this linkage, it is now limiting the motion of this 4 bar. So, what kind of a linkage is this overall? So, if I look at OD, okay, I have D, I have C, this should be, I should show with a, to show that this is one link, okay. There are two links there. This I have OA, A, B, say OB. So, this becomes my overall linkage once I add the driver dyad, okay. Now, which part should be the Grashof linkage? It should be, I should check the Grashof for OD, DC, OA, should be Grashof type 1 and ODD should be the shortest link of this 4 bar. Okay. So, now I could drive this with a continuous input. I could have a constant speed motor attached at OD. I could drive link ODD with that and have A1 B1 move between A1 B1 and A2 B2. Okay. So, I achieved motion generation with limits on the two positions by attaching these additional two links. So, what kind of a linkage is this one, this whole thing? Do you recognize? How many links? It is a 6 bar. What configuration? It is a watt. It is a watt configuration of the 6 bar. So, this is a, you have one 4 bar driving another. The output of OD DC OA is the input for OA AB OB. Okay. So, this is the Watts 6 bar solution to achieve this 2 position motion generation with limit positions. Okay. So, you have now synthesized a 6 bar for your application. Started off with a 4 bar, then in order to be able to drive it with a continuous input, you converted it into the 6 bar. This is called attaching a driver dyad. Okay. For a 4 bar, typically for a non-Grashof 4 bar, you can use a driver dyad, you can synthesize a driver dyad so that you can have a continuous input. Okay. So, just with the one thing that we learned to do, we have now extended it to multiple applications. Any questions so far? So, always after you synthesize, you check Grashof. In real life, you would also either build a model or simulate it over the entire range, because see, when you do this 2 position synthesis, all that it guarantees is that it can be assembled in those 2 positions. It does not tell you what is happening in between those positions. So, if you encounter toggle positions, for instance, I hope you remember what toggle positions are, when you can no longer drive the link with the same input, you can't drive the mechanism, it gets locked in that position. If you encounter that, then A1 B1 cannot move to A2 B2, and that is not something you can check from the synthesis procedure alone, because this only guarantees assembly of the linkage in the 2 positions. So, you would actually have to build a model or use some kind of a simulation package to check whether it is able to move from A1 B1 to A2 B2. Okay. So, that is something that that check always has to be performed when you are designing a linkage. If it is a Grashof, you do not have to worry about that, because it will be able to drive through the Grashof criterion ensures the rotatability. So, you do not have to check for toggle positions for that. So, this will be able to move from, but if this linkage has a problem, then if it was just this link, it can move it between those 2 extreme positions by use of this driver dyad. But whether it will be able to actually, whether this linkage will move from this position to this position, that has to be checked. The other thing that you might want to look at when you look at the effectiveness of your design is also the transmission angle. Okay. If you have forgotten what that is, please go back and look at it. So, the transmission angle for smooth operation should typically be greater than 40 degrees or so. Okay. It is the angle between the coupler and the output link which determines. So, again those are design criteria that you would check after the synthesis is done. Okay. To check whether it is a good solution. Later on you will see that when we do analytical synthesis, you will be able to specify some of these as criterion that you can then. So, with graphical analysis you are somewhat limited, because you solve something, then you analyze it to see whether it is a good solution. If it turns out, then you have to go back and do the procedure again. Okay. It is very quick, it is very intuitive, because it is simple geometry. So, it is very easy to understand how graphical synthesis works, and that is why it is very useful, because it can give you like very quick solutions. But in some cases, if you find that you have to go back again and again to the drawing board to do this, then this may not be the best way to synthesize your linkage. That is when we will go to the analytical methods, which are harder to set up. So, you would have to program all those equations, set, but once you do that, it is very easy to cycle through multiple solutions, and you can also specify criteria, you can check. So, you can build in the transmission angle calculation into your code. You can do all that when you are doing an analytical solution. So, here how many solutions are possible? What were our free choices? So, for A1 B1, so we said this is the rigid body, A1 B1 had to be moved to A2 B2. We assumed that A1 and B1 have to be the moving pivots. Okay. Moving pivots are also called circle points. Why is that? Because they trace, they are attached to the link which is pivoting about a fixed point, therefore, they trace, the path that they trace is a circular path. So, the moving pivots are A and B here, they are called circle points. OA, OB, also D, D is also a circle point. So, A, B, D are the circle points here. OA, OB and OD are called the fixed pivots or the center points. So, you will see this terminology used interchangeably. So, if I say center point, it means fixed pivot. Center point corresponding to point A, circle point A is OA. Okay, similarly, so circle points and center points are used interchangeably with moving pivots and fixed pivots respectively. So, if my circle points are fixed, A1 and B1, then okay, I do not have a choice then, but I do have a choice for OA, right, anywhere on the perpendicular bisector. So, I will have an infinity of choices for that. I will have an infinity of choices for locating OB. Okay. Then how many choices do I have for point C? Which has to be located on link OA, A. Why? It can, yeah, I could have this shaped any which way, right. So, I could choose this point C anywhere on this plane. Okay. So, I have, so let us say OA, I have an infinity of choices, OB infinity of choices, point C I have infinity square. I do not necessarily have to take it on OAA, I could take it anywhere on the body OA defined by the pivots OAA. Okay. So, that then if it is, if the timing ratio is given, if timing ratio equal to 1, then OD has to be on that line joining C1 and C2. Timing ratio is time for forward stroke by time for return stroke. Okay, here I was designing a driver dyad for timing ratio equal to 1. Okay. So, this OD has to be on that line. So, then my choices for OD, I have an infinity of choices. I can choose it anywhere on that line. Once I choose that, do I have a choice for D? No, D is now unique. D becomes unique because it has to be half of C1, C2. Okay. So, you can see I have, there are a lot of decisions I am making, lot of choices I am making as I am doing this synthesis. Okay. Lot of free choices that I have, which can give you multiple solutions. Okay. But you will find that if I choose OD very close to here, then I may not get a Grashof linkage. So, some of these intuitively I choose. Okay. Similarly, here, you know, if my choice of OA and OB, I could run into toggle positions if I choose in such a way that the configurations are different. Okay. So, that is something. So, unconsciously I am making some choices about suitable linkages, but it is possible that you may not come up with a suitable solution in the first try. So, for instance, in the exam, if you do all this and then you come up with a linkage that is non-Grashof, that is okay, because in real life you will have more time to go back and fix it. As long as your procedure is correct, I will not penalize you, okay. But you have to make sure that you follow the procedure and show what you are doing, okay. So, here if I look at for this linkage, I have OD, this is equal to, so my crank length is ODD, my coupler is DC, and the rocker is COA. It is not A1OA, because the linkage does not care what points I am taking beyond the pivot. As far as this linkage is concerned, the rocker is COA, and the fixed link is ODOA. Okay, so that is what you would use to compute the Grashof criteria. Okay. So, you would do that and then check for, because as far as this linkage is concerned, A is simply a coupler point. Okay, say sorry, A is simply a point, another point on the rocker. So, it is the kinematically the linkage is ODDCOA. So, this is for timing ratio of 1. Okay. Now, in many cases, as I mentioned earlier, if these are the two extreme positions, you can have, so in the case where the timing ratio was 1, we always took this pivot OA on the line joining B1 and B2. So, that should tell you that if OA is not on that line, then your time for the forward stroke and time for the return stroke are going to be different. So, here you can see the A1 to A2 traverses this angle, okay. A2 to A1 traverses a smaller angle. So, if I am running it with a constant speed motor, the time it takes to go from A1 to A2 is going to be, and therefore B1 to B2 is going to be longer than the time it takes to come back to from B2 to B1. Okay. So, this is called a quick return mechanism. So, a quick return crank rocker takes a different amount of time for one stroke than for the other stroke. So, let us say you are given a particular time ratio. So, if I look at it here, I can call this angle alpha, this angle beta. Okay. So, my time ratio is essentially alpha by beta, or I can look at it as alpha by 360 minus alpha in degrees. Okay. I will just explain this first and then I will explain the construction of the quick return mechanism. Okay. So, now I define a construction angle delta as mod of 180 minus alpha or mod of 180 minus beta. Okay. So, it is essentially this angle, that is a construction angle that I am going to use for the construction of this quick return mechanism. Okay. So, now if I look at this mechanism, so I have my construction. So, if I know the time ratio, I can find the construction angle. Okay. Now, if I look at this mechanism, these are the two extreme positions. These are the positions where the crank and the coupler are lined up, right, the two positions. One is folded on the other one they are in line with each other. Okay. So, here if I look at this, OA B1 is what? Is R2 plus R3. So, if I look at my 4 bar or my crank rocker and I designate this as 1, 2, 3, 4. Okay. 2 is generally my input link, here in this case a crank, 4 is my output link and 3 is the coupler. So, R2 plus R3 is OA B1 and OA B2 equals R3 minus R2, R3 minus R2. Okay. So, these are the, so if I solve these two I should be able to get, so if let us look at the construction of this. Oh, okay, I do not have, okay. So, I will just use this. So, I am given that I want to move a rocker through a certain angle theta, okay, using a crank rocker, and I want to achieve this with a time ratio which is given to me, non-unity time ratio. So, the first thing, I know the time ratio, so I can calculate the construction angle. So, I am given, so I pick some point, I know my angle that I want to move this through. So, I have this, okay, and I am given the time ratio. Time ratio is alpha by 360 minus alpha. So, I can calculate delta, say 180 minus alpha. Okay. So, now I have alpha. So, once I construct my rocker, I pick some point in the plane to locate my pivot OB, fixed pivot OB, and then I pick some length for the rocker and construct the two positions. They may already be given to you as design variables or not, or you may have to choose them. Okay. So, I can now draw any line through B1. Okay. Then if I look here, this is a line through B1. If I draw a parallel line through B2, this angle should also be delta. Okay. So, I would use that for my construction. So, if I take a parallel through here and then mark off my angle delta here, then this angle is also delta. So, this gives me what? What is this point? OA. Okay. Now, I have OA B1, OA B2. So, I know OA B1 equals R3 plus R2, OAB2 is R3 minus R2. So, from this construction I solve for R2 and R3. Okay. Once I solve for that, then I can construct the, so I will know R2, so I can just so this would be my A1, this would be my A2. Okay. So, this completes my construction for a quick return. Now, again my mechanism is OA, A1, B1, OB. Check, Grashof. Okay. The other thing about this kind of a mechanism is it does not matter what scale I choose initially. Okay. We are talking about, yes, sorry, yes, it will be, this is delta, this is okay. This will be A2, this will be A1. Check. So, I was saying, so I can scale this entire linkage up or down without affecting any of, I will not affect the time ratio, I will not affect the angular relationships. Okay. So, I can design a crank rocker. So, I may be designing something that is for an application where I have really large links, but for this, for my graphical synthesis, I can choose a suitable scale. In the previous case, for the motion generation, that is not possible, because when you are talking about motion generation, you are talking about a certain location and orientation of a rigid body in the plane. Okay. So, that will change. Okay, that if I change the dimensions of the links, okay, where I have, unless I just the driver dyad part of it I can expand or contract, but that part of it cannot be changed. So, that part of the 4 bar cannot be changed, this has to stay the same. I cannot change the scale of that, because I am talking about the position and orientation of the rigid body, the absolute location and orientation in the plane. So, for motion generation I cannot change the scale of the linkage that I design and expect it to perform the same function. For function generation, or if I am just looking at rocker output, angular inputs and outputs, then by all means I can change the scale of the linkage and still retain the input output relationships. Okay. It is important to remember that. So, this is how you design a quick return crank rocker. Okay. Again made a lot of free choices. For instance, this line that I drew through B1, I just took it at random. I made a free choice there. Next we will look at how I can actually have a certain offset. So, in this case what I would do is, if I wanted a certain orientation of OA and OB, I would just design my linkage, then reorient it, provided I had flexibility in reorienting the rocker output. So, if this gets fixed, then again I do not have that same flexibility. Okay. Only if this is not fixed, then I can reorient the linkage, still get the same travel. The change in the angle is okay, that does not change when you scale the linkage up or down. Okay. So, that is, I can do the same thing with a slider crank. The slider crank is just a special case with the rocker pivot at infinity. So, here B1 and B2 are points on a straight line. Okay. So, if I have B1, B2, in the previous case they were points on an arc pivoted about OB, here they are on a straight line. So, I could design a crank rocker, a slider crank in the same way as the crank rocker, again with B1 and B2. Okay. Here this would be my construction angle delta. Okay. Everything else remains the same. Again OA B1 equals R2 plus R3, OA B2 equals R3 minus R2. Okay. And we did not look at, so the slider crank also has, just like the Grashof criterion, you have some conditions so that the slider crank can be assembled in the extreme position. So, if you have, what kind of a slider crank is this? This is called the offset of the slider crank. If this center was in the same line as your B1, B2, okay. So, that is similar to your timing ratio 1. So, this moves 180 degrees, that moves 180 degrees, that is called an inline slider crank. So, when you have an offset slider crank, you automatically have a timing ratio that is not 1, you have a quick return mechanism. Okay. Now, in the case of the slider crank, the offset is an important parameter and it can also determine whether or not you will have a functioning linkage. So, there are some, just like the Grashof criterion, for the slider crank you have conditions such as R3 should be greater than R2 and then R3 minus R2 should be greater than your offset. So, these are conditions that apply to a slider crank mechanism. So, that is something you should be. So, in the case of quick return slider crank, in many cases the offset will be specified. Okay. So, in that case, so here we have chosen, all these were free choices. The only thing I had was this stroke. So, instead of the rocker angle there, for the slider crank I am given the stroke of the slider. I use that and the timing ratio, so the delta based on the timing ratio to design this. Okay. So, if I take a random line through B1, I am going to get some offset. Okay. If I fix one more thing in the slider crank and then, so I get an offset, I get these two equations which determine R2 and R3, because once this is OA is fixed, these become fixed. Okay. So, I can draw an infinity of lines through B1, okay, and that will give me an infinity of solutions. Okay. Now, if I fix one more thing in the slider crank, then my solution becomes unique for a given stroke. Okay. If I am given the stroke and I am given the timing ratio and I fix, say, the offset R2 or R3, then my solution for the slider crank becomes a unique solution. So, let us just look at the case of specified offset. Yes.
The timing ratio limited in due to some constraints.
Due to?
Like the inequalities we saw.
Yeah.
The timing ratio was limited to something.
So, the timing ratio is usually a design requirement. So, you have to make sure that you design for that, right, and then you check whether your design meets these conditions for it to be, for the slider crank to be able to be assembled, okay, to go like the limits of assembly for the slider crank. So, that is exactly what we are coming to next. So, if you have, so if I specify the offset, okay, to, then what are my options? So, I know that maybe I do not want such a big offset. Okay. So, instead of trial and error, I say, okay, look, I really need the offset to be no more than or to be a certain quantity, and then I want to design for that. So, for that, what we are going to, if you look at this angle delta, okay. So, if I look at B1 B2, okay, and I look at this angle delta, right, essentially I could create these sort of triangles, right, with this angle delta. What is that? The locus of this point OA is going to be a circle. It is going to be a circle where your chord makes an angle delta on the circumference, which means it has a central angle of 2 delta. So, if I construct the circle for which this chord makes an angle 2 delta at the center, then I get this infinity of choices on the circumference of the circle to get my to find my offset. Okay. So, that is essentially what this construction does. So, how do I construct the circle? So, I have B1 and B2, draw the perpendicular bisector. Now, I know the angle delta. So, from the vertical I do this. So, that delta I take it like that, I construct this line. So, where it intersects gives me the center of the circle on which OA will lie, such that if I pick a point on that, I will always get that timing ratio that I want, because the timing ratio is a design parameter, it is a requirement. Okay. So, once I find the center of the circle, obviously B1 and B2 have to pass through that circle. So, I know my radius, I construct this circle. So, this is the circle on which OA will lie. That is my infinity of options for OA, any point on that circle. So, now if I specify an offset, it is very easy. I know my line of the line in which the slider moves, okay, B1, B2. So, from there whatever my offset is, I mark it off on that circle. So, this is my specified offset, say epsilon. Okay. So, it could be here. So, if my offset was specified here, then this would be my OA. Something else, anywhere on that circle I take the perpendicular distance from the line of action of the slider, and that gives me the location of OA. So, that is right. So, you would take this as the major segment of the circle, okay, delta. You are assuming that OA lies, you will still have an infinity of solutions even if I am not considering the other part of the arc. So, obviously, if you are not going to pick OA here, because then your central angle is different. Okay. So, this gives you the unique solution. Now, for a specified offset I get a unique solution, because once I know the circle, once I specify the offset, I know exactly where point OA lies. Okay. You could say it could be on this side, but still it is considered a unique solution, and then OA B1 will be your R3 plus R2, OA B2 will be R3 minus R2. Okay. So, this will give you the solution for a slider crank with a specified stroke and timing ratio. So, specified offset, stroke and timing ratio are also given, are the design parameters. That is what you are designing for, are the design. Okay. So, we will stop here and continue in the next class with the other cases where we are specifying, instead of say the offset, we will specify R3. It is all based on fairly simple geometry, it gives you an idea of the choices that you